So this notion of countability applies to whole numbers, integers, prime numbers. It also applies to rational numbers, fractions like, a over b. Lots of things are countable, but there are some things that are a larger infinity than the whole numbers. And in particular, when we have real numbers, and we use this funny looking r to represent the set of real numbers, the size of the real numbers is actually bigger than the size of the integers, or the whole numbers, aleph-nought. Right? It's a fundamentally larger version of infinity. I'm not going to prove that here, but if you want to see a proof for it, look up Cantor diagonalization. It's a very clever, pretty simple proof to put together, and it describes a general method, this diagonalization idea, that can be used to do a lot of interesting proofs of things. It's a way to say, okay, suppose that the size of the reals is the same as the size of the whole numbers, and then it develops a contradiction. So that's a fun thing to look up on Wikipedia or whatever you like. But the punchline from that is the reals are a fundamentally bigger set of things than the whole numbers or the integers. And we can sort of imagine this is the case if we just kind of do a few thought experiments about real numbers versus whole numbers. So for example, let's make a number line with 1, 2, 3, 4, 5, right? So these are whole numbers. And if we ask, for example, starting right here at the number 3, what is the next number in this sequence? Well, it's the number 4. And if we start here with the number 6 and we say, what's the next number? It's the number 7. And if we say, what's the first number in this collection? Well, it's the number 1. Okay, but now imagine that we have real numbers. So, here's 1, 2, 3. But here's, 1.5, and here's 1.6, and here's 1.1, and so on. And so every, real number that we can think of, a number, something point something, just think of this region between 1 and 2. Okay, so first of all, there's an infinite number of real numbers between 1 and 2, because we can just, take one point and we can write out any string of digits we want, and there's a real number. But the really interesting thing is if we say, okay, in this region between 1 and 2, what's the first real number that comes after 1? There's no way to answer that. There is no next real number. There's an infinite number of things that come after 1, but there's no immediate successor to 1. And maybe it's, 1.001, but no, that's not the case, because in fact, this number comes before that. Was this the number right after 1? No, because this number comes before that. And any number that I pick that comes after 1, even something really close to 1, there's an infinite number of numbers between 1 and that thing that I picked. So there's no immediate successor to 1 in the set of reals. And that's different from the set of whole numbers, integers, primes, things like that. And this ties in directly to countability. If this set was countable, we could make an assignment where 1 goes to a number, 2 goes to a number, 3 goes to a number, and so on. And we could say, okay, so what's the next number after 1? Well, maybe it's the thing that 2 maps to. But we can't do that with the reals. And that's a hint that there's something sort of fundamentally different going on with real numbers. So that's something we're going to want to keep in mind.